Okay, thank you. Yeah, so welcome back to part 2. We are now going to start proving some very technical results on solid bricks. And as I mentioned earlier, some of these results are used later to prove Lovaas's conjecture that every brick except K4 prism in the Peterson graph has a beam-variant edge, right? But that we may see eventually, hopefully someday, right? So, what I'm going to do today is I'm going to, so let's continue with some of the things we have been seeing. We discussed what non-removable edges in a bipartite matching chord graph looks like. We also saw what mutual dependence looks like in a brick, for example, right? But what is mutual dependence? Well, mutual dependence is a case where both edges are in particular non-removable because the other one depends on it, right? So there is a nice result which I'm not going to prove today, which I'm not going to present the proof of today. It's about a characterization of non-removable edges in bicritical graphs. Bicritical includes bricks, right? Bricks are 3 connected bicritical graphs. So we are going to state this result, maybe do a couple of examples, and then prove some corollaries of this result. And then hopefully in the next lecture on Wednesday, we will have enough time hopefully to prove the result. Yeah. So this is recall. Dulmage-Mendelssohn barriers strike again. Yeah. So what is a DM barrier? In a matchable graph, recall that this was defined in general for all matchable graphs. Does anyone recall what a Dulmage-Mendelssohn barrier is? Well, we all know what a barrier is, at least in a matchable graph, yeah, or even otherwise. So what's a Dulmage-Mendelssohn barrier? And we use Dulmage-Mendelssohn barriers to prove the ELP theorem. So we want the core to have some property, and we want the odd components to have some property. Odd components should be hypomatchable, and the core should be matching covered. The core should be matching covered, right? So a Dulmage-Mendelssohn barrier is a barrier with the following properties. The core is matching covered, and of course core is always bipartite. And each odd component, it's crucial to note that there may be even components, right? Each odd component of G minus B is critical, also known as factor critical or hypomatchable. Yeah, that's what a Dulmage-Mendelssohn barrier is. So it turns out that non-removable edges in bicritical graphs, they have some structure that is related to the existence of a Dulmage-Mendelssohn barrier in some graph. Okay, and we'll do some examples to see this situation. So this is 10.1. G is a bicritical graph. F is a non-removable edge. I'm going to call it E. I don't like F. E is a non-removable edge. Well, because it is not removable, when I delete the edge, the resulting graph is not matching covered. Therefore, there are edges that are not matchable. Therefore, there is a barrier that will contain the ends of such an edge. Right? Okay? So the statement is then G minus E has a barrier, has a Dulmich-Mendelssohn barrier with some nice properties, more than what is already there. Has a Dulmich-Mendelssohn barrier B let me just make a drawing. So let's say this is my barrier. Let me put some space. This is my graph G minus E. So I have odd components. There may also be even components. Yeah. And the edge F let me use a different color. F has its ends in distinct odd components of E. E has its ends in distinct odd components of G minus E minus B. Okay, nothing so far. That's one property. And the other property I want is that every odd component is the shore of a separating cut in the original graph G. This sounds very similar to some other things you have done before. In that case, we had the shore of a tight cut, right? But anyways, so for every odd component, if K is some odd component, including these components, then partial of K is the shore of a separating cut in G. So what are the two properties? E has its ends in distinct odd components of G minus E minus B, and secondly, for every odd component K of G minus E minus B, partial of K in the graph G is a separating cut in G. Let's look at some examples. Yeah? Is it clear? Okay. Let's see if we can make some examples. So for any bicritical graph, any non-removable edge. So of course I can do K4, but K4 seems a bit boring. Let's do prism. Every edge is non-removable, so I can do this for any edge. Yeah, I don't know which one. Shall we try this? This is G. What we want is a barrier in G minus E. Can you all try to find the barrier? It should be a Dulmich-Mendelssohn barrier, and it should have these additional properties. See if you can find it. I haven't found it. Right, so the point is that because it is not a removable edge, in the resulting graph there are edges that are not in any perfect matching. So you should consider such an edge. That is one way to think about it. That is at least one starting point. Right? So that the only such edges are 0, 2 and 3, 5. So that means there should be a barrier containing 0 and 2. Right? So you can try to think from that point of view. Of course, the barrier you try may not work, but then, well, it's a 6 vertex graph. Right? So if you just try 0, 2, actually it works. Observe that 0, 2 is a barrier, and the only components are actually odd components in this example. 1 is a odd component, and 3, 4, 5 triangle is the other odd component. And what is the core? Core is C4, is it? Core is C4. Yeah, core is C4. That's matching covered. And the odd components are factor critical because it's K1 and K3, so they are hypermatchable graphs, right? And the edge 1, 4 is going from one odd component 1 to the other odd component 3, 4, 5 triangle, and each of these is the shore of a separating cut. One of them is trivial. Well, trivial cut is separating cut, and the other one is the triangle 3, 4, 5. That is the only non-trivial separating cut in the prism. So this example checks out. Yeah. Okay. So we are not going to prove this today. We will assume this and prove more things. So then we will hopefully be motivated to prove this. Okay. So consequences. Good. So you have shores of separating cuts. Here you have separating cuts. Well, in a solid brick you don't have non-trivial separating cuts. Therefore, in the case of a solid brick, we should be able to say something stronger, right? So what would happen in the case of a solid brick? What can you say about all these components? They should just become trivial, right? So 10.4. So now I have a solid brick. An edge E, if an edge is non-removable, then actually basically the same thing, each odd component will just become trivial. Then G minus E has a Dulmage-Mendelssohn barrier such that each odd component of G minus E minus B is trivial, and E has its ends in distinct odd components of G minus E minus B. Our drawing probably is much better. We have something much nicer. We have this set B, we have this set of isolated vertices in G minus E minus B. There may be even components, that has not been forbidden, but the edge E looks like this. Maybe I'll draw it in yellow. This is what non-removable edges in a solid brick look like, right? Now what we'll do is we will get more consequences. Yeah. Okay. So the next thing we'll do is we will try to characterize pairs of adjacent non-removable edges, and we will conclude that actually at every vertex there can be at most two such edges. At every vertex we will prove that there are at most two non-removable edges incident. The other edges are actually going to be removable. Yeah? And this should start sounding very similar to Lowas-Zampala. In the case of Lowas-Zampala, we considered a bipartite matching chord graph, and we considered a bunch of non-removable edges incident at a common vertex. In fact, what we first did is we just looked at two non-removable edges incident at a common vertex. Does everybody remember that? We got two drawings and then we were able to make some more inferences, and we were able to get a nicer drawing for k non-removable edges incident at a vertex. Yeah, so that's sort of where we are heading. But now we are not in bipartite graphs, we are in solid bricks, also known as Birkhoff or Neumann bricks. They have properties similar to bipartite graphs. For example, they don't need Edmonds odd set constraints. Right? So that is sort of one way of looking at solid bricks. Although they are bricks, they share a lot of properties or sort of similarities with bipartite graphs. For example, solid bricks are exactly those bricks that do not have a conformal odd bicycle. So there may be odd cycles, there may be vertex on odd cycles, but not conformal put together. Yeah. So okay. Maybe let's do so what we'll do is we'll just try to consider a solid brick with two adjacent non-removable edges and then try to do some analysis from there. So let's say right, so this is QED, immediate consequence of this. So next thing is pair of adjacent non-removable edges in solid bricks. So let's consider I have a solid brick G . And let's say I have I have some vertex V, and two of the edges incident at V are non-removable. V and VV1 and VV2 are both non-removable edges. Okay, good. Before we go here, let's actually do a couple of examples of this also, right? So we did examples of this one, but there we took prism, which is not solid. I just want to do a couple of examples of solid bricks with non-removable edges, right? And then we'll go here. So what's your favorite solid brick? Not too small, slightly bigger than too small. Huh? W5, I like. W5 is a nice brick. Yeah, that's W5. What are the removable edges in W5 and what are the non-removable edges? Spokes are removable and the rest are non-removable. So let's pick a non-removable edge maybe 2, 3. 2, 3 is a non-removable edge. So therefore, this should happen. Can you all give it a shot? See if you can make this drawing of W5 with respect to the given edge E. And if you finish that, then we'll do one more. The next solid brick I'm going to choose is the Murthy graph. But here I'm going to ask you to first figure out what are all the non-removable edges. And if you find one, then make the drawing with respect to that edge. Yeah, so let's complete the first example. So the barrier is indeed, when you delete the edge E, these three vertices, 1, 5, 4, that is your desired barrier. Right, let's make a nice drawing. Why not? So 4, 5, 1, 0, goes nicely here, and 3 goes nicely over here, and 2 goes here. Oh, this is 0 and 0. Okay. And let's see. So now I can just complete the graph, right? Because 5 is my hub, and I need a 5 cycle on the remaining graphs. 5, 3, 4 to 3 to. Oh, I see. 4, 3, 2, 1, 0. When you delete E, this is your barrier, and it has all the properties you want. All the components are isolated. There happen to be no even components in this case, and the edge E has its ends in distinct odd components, as it should have. Yeah. Okay. So this is the W5 situation. And see if you can also complete this one. Find all the non-removable edges, and then pick your favorite and figure it out. Right. So one thing worth noting about this graph is it's helpful to remove this edge and then understand the rest of the graph. The rest of the graph is just K4 splice K33. So that can generally help you to figure out the removable edges. And in fact, H has this very nice property. It's a solitary edge. There's only one perfect matching containing H. If you take H in a perfect matching, you have no choice in life but to pick all these 3 edges. These 2 facts are helpful. But I'm good. I just came to the cat was flat. Yeah. Okay. trapped in the building. I just released it outside. Maybe the second one. Okay, anyone? Yeah, so using the fact that if you delete H, then you just have K4 splice K33, and using this perfect matching that is shown in yellow, using these two facts you can conclude, with not much work from there, that the only non-removable edges are actually the edges in the non-trivial 3 cut. Right? The triangle edges are actually removable now, but the non-trivial 3 cut 2, 5, 3, 6 and 4, 7, those are the only non-removable edges. So of course that is a symmetry there, so I picked my favorite here, E. And if I pick E as 3, 6, then actually, if I'm not mistaken, there's probably only one such barrier. I'm not sure. The one I found seems to be the one everybody else found. So that is 5, 7, 0, 1. In G minus E, where E is this edge, if you delete 5, 7, 0 and 1, then all other vertices 2, 3, 4 and 6 are actually isolated. Sorry? Oh, instead of 0, 1 I can take 2, 4? Oh, I can take just 2 and 4. Oh, I see your point. Only 2 and 4. If I take only 2 and 4, then this becomes one odd component and this becomes my second odd component. Huh.
We want odd components.
But we also want the odd components to be trivial. Okay, so then there is only one. Yeah, good point. So yeah, if you just apply this, wait, what happened? How did we get? Because then they should have been separating cuts, no? Wait a second. Then maybe some property should fail here. They are factor critical because they are K3, but the bipartite graph should not be matching code. Can you check? Okay. Wait. I see. The result says that there is a Dulmich-Mendelssohn barrier which has these properties. Okay, let's just make a drawing. Yeah. Okay, so let's do the drawing. I'm going to erase E. Okay. G minus E. Let's draw both of these barriers. One is 2, 4. Yeah. If I remove E and I delete 2 and 4, then 0, 1, 3 is one component. Three maybe here, and 0 goes to 2, and 1 goes to 4. Okay, maybe like this. And 5, 6, 7 is another component. Yeah. Okay, let's complete the whole drawing. 5 goes to 2, 7 goes to 4, and 0 is adjacent to 2, 3 and 4, therefore here and here. 1 is adjacent to 2, 3 and 4. Yeah. And this is my edge H, and the edge we removed is 3, 6. Yeah. Okay. Good. So let's see what happened. We have a bicritical graph. We have a non-removable edge. Then G minus E has a Dulmich-Mendelssohn barrier such that the core is matching covered. What's the core? The core is, in fact, there are all possible edges. Therefore, it is C4 up to multiple edges. The core is matching covered, and each odd component is critical. That is true. Each odd component is critical. Yeah. Okay. That is just Dulmich-Mendelssohn. Okay. E has its end and distinct odd components. True. This condition fails. The theorem says there is a barrier where this condition actually is satisfied. Good. I think we are appreciating this statement more. Right? So, it is not true that any barrier that satisfies 1, 2 and 3 also satisfies 4. The theorem is saying that there is a Dulmich-Mendelssohn barrier that has all the 4 properties you want. Yeah? So this is not that barrier. Because we are not getting separating cuts, because it's a solid brick, it should not have any non-trivial separating cuts, and it doesn't. Yeah? So that also tells us that this is going to be non-trivial to prove. Right? If you want the 4th property, you need to do something. Questions, concerns? Yeah, so I had not actually tried this myself. I had tried the convenient barrier. Yeah. So now let's try the convenient barrier, right? Which is the one that the theorem should actually give us. And let's draw the graph with respect to that. So now we'll do 0, 1, 5, 7. Yeah, and I think I was not able to find any nice way to draw this. So whatever. 0, 1, 5 and 7. And 2, 3, 6 and 4 right now. Okay. Let me draw the bipartite graph. 2 has edges to 0, 1 and 5. 3 to 0 and 1. 6 to 5 and 7. And 4 to 0, 1 and 7. That's the bipartite graph. Let's draw the other edges. 0 and 1 are adjacent. 5 and 7 I believe are adjacent. and the edge we removed is 3 to 6. Now observe that every vertex has degree 3 and 2 vertices of degree 4. That's the Murthy graph. Yeah. So now this is a barrier that has the properties we want, right? And the properties we want are actually this one. We want all the components to be actually isolated, single vertices. The reason that will happen is because we will first apply this theorem. Now because these are non-trivials, these are going to be separating cuts, all the components should in fact be trivial components. Otherwise you would have a non-trivial separating cut. Yeah? Okay, good. Is the content of this clear? Yeah, so we saw two examples, W5 and the Murthy graph. Yeah, okay. So now what we'll do is, the point is for every non-removable edge, you get this nice, almost bipartite looking graph. It's not really bipartite. There are edges in the barrier. There may be edges in the barrier, in fact there should be. And the edge E, of course, has both its ends in the other color class. Right? So it's not really bipartite, and of course there may also be even components. But if we have two non-adjacent removable edges, two adjacent non-removable edges, then you will get two such drawings. One for the first edge, one for the second edge. Right? Can we make more conclusions from here? That's the next part. Okay? So that is where we are heading next. Yeah? Turns out when you have two such edges, the picture is much more constrained. Yeah. And of course, one example would be W5. Take two edges of the rim that are adjacent. And if you make the drawings, you will get something much more constrained actually. Okay. But I will erase these examples and just focus on this next thing. Or maybe should I erase... I don't need this stuff anymore. I don't need 10.1 anymore. Yeah, all we need now is 10.4, which is a consequence of 10.1. Oh, all good? Okay. Alright, so now we have a solid brick, we have a vertex V, and we have two non-removable edges incident at this vertex, VV1 and VV2. Let me call them E. EI is VVI. So E1, V2. So we can apply 10.4 to each of these edges and make a drawing. There may be even components. Yeah? Let me draw some hypothetical even components, and everything is hypothetical except for what we know. Okay. This is my drawing with respect to E1. Let me call this B1. And the edge E1 looks like this if I put it back. One of the ends is V and the other end is V1. Let me call this fellow V and let me call this fellow V1. Yeah. Let's make one more drawing. This is B2. This is the edge E2, and this is V. This is V1. Sorry, V2. And there may be V1 components. Yeah. All good? These are just two drawings of G with respect to the two non-removable edges E1 and E2. Well, let's try to figure out the vertices we already know. So we have this vertex V. This is V1. This is V2. And since it is a brick, there is at least one more neighbor, V3. But of course, we don't know how many neighbors. There could be many more neighbors. VD, where D is the degree of vertex V. Yeah. But we know that V1, V2, V3 are there. V1, V2 is in fact the edge E1. And VV1, VV2 is the edge E2. And then there are more edges, at least one more. So let's try to figure out where these vertices are in the other drawings. Right? So we know V and V1 are here. Where is V2 in this drawing? Has to be in the barrier. V2 has to be in the barrier. And there's also V3. Where is V3? Also in the barrier. Yeah? Because this is the only edge that has its ends in odd components after deleting the edge and the barrier by definition of components. Yeah? So therefore, V2 is here, V3 is here. In this drawing, V1 is here and V3 is here. Yeah? So far so good? No lies? No lies? Yeah? Everybody convinced? Yeah. Remember, when you delete the edge and you delete all edges in the barrier and you delete the even components, you have a bipartite graph, also called the core. Right. So this is the situation. The two barriers in particular have at least one vertex in common, namely V3. There may be more vertices, but I have not drawn them. We don't know whether they exist or not. We know V3 exists. Okay, so I'm going to pose a question, a slightly more general question outside of this context. We have a bicritical graph, right? This is a solid brick, in particular it's a bicritical graph. And yeah, so here is the question I want to ask you. G is a bicritical graph. E1 and E2 are two adjacent edges. E1 and E2, I'll just make a small drawing. E1 and E2 are adjacent edges. And in each of them, in G minus EI, I have a barrier BI. G minus EI has a barrier BI, non-trivial barrier. Can we conclude that these are non-trivial? That's clear, right? Each of them has at least two vertices. Remember, G is bicritical. Therefore, G should not have non-trivial barriers. But G minus EI may have non-trivial barriers. My conclusion, my question is, what can you say about this quantity? can you make some conclusion regarding the intersection of these two barriers? One is a barrier in G minus E1, the other is a barrier in G minus E2. G is bicritical and they are adjacent edges. Can you make some conclusion regarding B1 intersection B2? You can probably see where I am going, right? We know that B1 intersection B2 contains V3. That much is clear. I'll give you a small hint in case you are stuck. Okay, I'll give you one more hint. Can it be at least 2? Is this possible? This is what I want you to think about. Supposing the two barriers B1 and B2 have at least 2 common vertices, can you try to arrive at a contradiction? Okay, anyone else? Okay, remember the graph G is bicritical. In G, if you delete any two vertices, the remaining graph is a perfect matching. Supposing there are two common vertices x and y in B1 and B2. So x and y belong to B1. B1 is a barrier in G minus E1. And x and y also belong to B2. B2 is a barrier in G minus E2. So now using this fact, what can you conclude? In G minus E1, there is a barrier containing x and y. In G minus E2, there is a barrier containing x and y. but G minus X minus Y has a perfect matching. So how is this happening? There is a perfect matching in G minus X minus Y, but in G minus EI minus X minus Y, there is no such perfect matching. Right? Because in G minus EI, there is a barrier BI that contains both X and Y. Right? So, what does that mean? In G minus X minus Y, there is a perfect matching. So, what do you conclude about this perfect matching? So the point is G minus X minus Y has a perfect matching. Take a perfect matching, M. But in G minus E1 minus X minus Y, there is no perfect matching because there is a barrier containing X and Y. In G minus E2 minus X minus Y, there is no perfect matching for the same reason. What does that mean? Why is that perfect matching disappearing if I delete E1 or E2? Well, the only way to disappear is if it uses the edge E1 or E2, right? But that means it uses both the edges, but they are adjacent, right? So that perfect matching M must use E1, it must use E2, but E1 and E2 are adjacent. Therefore, this is not possible. Yeah? So, in this more general situation, we concluded that this is not possible. Therefore, the intersection has to be at most 1. This is one of the lemmas. I think this is 10.5 or 6 or something. Yeah. Now we'll go back to our situation here, whatever this is. Yeah, what we are trying to prove is 10.5, which I have not written. Yeah. So here, we found a common element in the intersection of B1 and B2. Now we can apply this and conclude that the intersection is only that vertex. The intersection is only that vertex. There can't be any other vertex in the intersection. So now, B1 intersection B2 is exactly the vertex B3. What does that tell you? What does that tell you about the degree of the vertex V? 3. Because all the neighbors of V, except for V1 or V2, depending on the drawing you are looking at, they are anyways in B1 and in B2.
Running low on battery, so we should switch.
Oh, okay.
You can choose.
Sure, switch now. Alright, thank you. So yeah, back to where we were. We concluded that the intersection is exactly this vertex V3. Therefore, there are no other neighbors of V. We have already concluded that the vertex V has degree 3. Right? So this implies that the degree of V is exactly 3. So we are in this situation. V has no more neighbors. Let me just put a 3 over here. Yeah, okay, fine, we got more information. Okay, but now, using this fact, we can actually conclude more things. See if you can conclude more things and make this drawing somehow even more precise. You can probably tell what I don't like in this drawing. Right? there is something that I don't like in this drawing. Right? I want to get rid of the things I don't like. For any two barriers, B1 and B2, not just this B1 and B2, for any two barriers B1 and B2 of G minus E1 and G minus E2 respectively, we know that the intersection is at most 1. Yeah? Using that, can you get more information? Even if you haven't been able to sharpen it, you can just tell me what you want to do. Right? So, what is the sharpening that you are looking for? Right? Just guess, and then we will talk about it further. There are stages of sharpening. We will do one more sharpening after that. So I'm looking for the preliminary sharpening. Yeah, so the sharpening we are looking for is I want to erase those boxes, right? Those even components, I want to erase them. Basically, I want to prove they don't exist, right? So we'll try to do that. I'll give you one small hint in that direction. Any even component has an edge. Yeah. Supposing there is an even component in one of these two drawings, then it will have an edge. X, Y. Now try to make progress from here. Okay, so I'll just make this drawing a bit bigger. I realize it's a bit too small. So this is one even component that we are focusing on. It has an edge. Let's say xy is some edge. Maybe I'll just draw with white, okay? So see if you can figure out what are the different possibilities for x and y in this drawing. I mean, they are both drawings of the same graph, right? So the two vertices x and y have to be there somewhere. And for every single case, arrive at a contradiction to for every single case, see if you can construct barriers from the existing barriers to arrive at a contradiction to what we have already established. Okay, so the point is, you think about where these vertices are in the other drawing and observe that given a barrier, this is in general true in life, given a barrier, if you take a vertex from an even component and you add it to the barrier, you have a barrier again, right, in a matchable graph, because anyways we know the number of odd components cannot be greater than the number of vertices you're deleting. So you will get at least one more, therefore exactly one more. Yeah. So I can always throw x into this and get a barrier containing x. This is true for any vertex in any one component. So therefore, if x is in one of the even components in this drawing, then I will take b1 plus x, b2 plus x, barriers of G minus E1 and E2 respectively, intersection is at least 2, contradiction to the lemma. Yeah. So therefore, x cannot be here. X cannot be here. In fact, if x is here also, same thing works. b1 plus x and b2, intersection at least 2, contradiction. So x cannot be here. X cannot be here. X cannot be here. X better be here. Yeah. Well, x and y are the same. There is no difference. Y cannot be here. Y cannot be here. Y better be here. But now you have an edge between x and y. Well, I thought these are odd components in G minus E2 minus B2 contradiction, right? So therefore, we have sharpened the figures. Yeah? But of course, now there's a counting problem according to the numbers I have chosen. Right? Here there are 8 vertices, there are 10 vertices. So let's fix that. Yeah, the situation has to be like this. Yeah, but now we'll get more information. Now these are B1 and B2. I'll call these, I can call them I1 and I2, which is what Lucchesi-Murthy typically do because they are the isolated vertices after deleting a barrier. I'll just call them A1 and A2. Yeah, okay. So this is my set A1. This is my set A2. Yeah, okay. So we have much more information. Basically, when you delete the edge EI and you delete all edges from the corresponding BI, all edges with both ends in BI, then you have a bipartite graph. Yeah, okay. Let's get more information. Yeah, so sharpen further. Use the existing sharpening to sharpen further. Can you relate these 4 sets with each other in some way? I don't know what way, but yeah, figure it out. Right? They are the same graph. Both of these are drawings of G. So, yeah, should be something going on here. See if you can figure it out. In fact, we already know that B1 intersection B2 is only one vertex. Oh, that actually settles everything. Right? Don't forget what we already know. B1 intersection B2 is simply one vertex V3. This is very useful. From here you should be able to conclude, you should be able to relate B1 with A2 and B2 with A1, right? Like a formula. Okay, if you have the formula, write it down. Right, so note that all these four sets are equi-cardinal. Right, there is no other possibility. There is n by 2 vertices here, n by 2 here, n by 2 here, n by 2 here. And you know that the intersection of B1 and B2 is just one vertex. What does that mean? Well, where did the other vertices of B1 go? They can't be here except for V3. So therefore all the other four vertices I have drawn in this set, they must be here. Yeah? Now you can write down an equation relating B1 and A2. So basically what you want is B1 is equal to A2 blah 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 and B2 is equal to A1 blah blah blah. Observe that the intersection of A1 and A2 is also going to be only one vertex. Right? One way to think about it. I think this is a counting argument that you had earlier at one point for something else you are doing. If I break this into two n by 2 parts, two halves, and I break into two halves, and if the intersection of, if this part has only one vertex, then it follows that this part also has only one vertex. That was a counting argument you used, I think Amit used for something we were doing last week. I was doing something more complicated using matchings and all. Right? So yeah, that's a fact. Right? So therefore if the intersection of these two is just one vertex, then the intersection of these two is also one vertex. And that one vertex we know, it's V. Yeah, now you can all see this. B1 is simply A2. You remove V and you include V3. Yeah. And B2 is simply A1 and you do the same business. You remove V and include V3. Yeah, did I make any mistakes? Correct? Okay. So that's what it is. Yeah. So we have a lot of information now. We took two non-removable, adjacent edges in a solid brick. We had something like this once upon a time, right? We had this kind of figure, and because we have two adjacent non-removable edges, we were able to sharpen both figures to this situation. Yeah. Okay. Few more things. We know that B1 and B2 will actually have edges. B1 and B2 are not going to be stable sets. That is clear, right? Because this edge has to be in some perfect matching. So definitely B1 and B2 can't be stable sets. Any perfect matching containing this edge must contain some edge joining two vertices in B1. Yeah? Yeah? So where are all the edges in B1 or in B2? Can we sharpen that further? We know there are edges in B1, we know there are edges in B2. Can we get more conclusions regarding where these edges are in B1 and in B2? Yeah, sharpen further. Where are all the edges in B1? Can we say something more about these edges? And likewise for B2. So note that A1 and A2, they are almost stable in the sense that they have exactly one edge inside. But B1 and B2 we don't know. We know they are unstable. We don't know how unstable they are. Yeah. So note that all edges in B1 must be all edges that have both ends in B1. They must be incident with V3, because if the edge is not incident with V3, then actually the edge has both ends in B1 minus V3. B1 minus V3 is exactly A2 minus V, but A2 minus V is almost stable except for this edge, right? And this edge is actually here. This is E2, this is E1, this is E1. Yeah. So therefore, every edge in B1 that has both ends in B1, one end has to be V3. And likewise, every edge here, one end has to be V3. This is what the situation looks like. I don't know what the other end is. One end is V3 for sure. Yeah. Okay, let me see. Did I cover all the points? Let's see. Yeah. Solid break. One more thing. Okay. Yeah. The only thing that I haven't mentioned explicitly is that if you delete all the edges that have both ends in A1 or both ends in B1, then you have a bipartite matching covered graph. And same here, right? That is because Dulmage-Mendelssohn barrier. We use 10.4 to get both of these drawings. Therefore, what you have here is actually a bipartite matching covered graph plus one edge here plus a bunch of edges incident at V3. Same here. Yeah? Okay? Good. So these are all the points. I'm going to quickly mention a few corollaries that you can try proving on your own now. But we will do that, you can do that later. So, this was 10.5, 10.6 was the lemma, 10.7 and 8. I'll just write down these two corollaries and see if you can prove them on your own later. In fact, they are exercises in Lucchesi-Muti. In a solid brick of order 6 or more, which means not K4, every vertex is incident with at most two non-removable edges, therefore at least one removable edge. So this is 10.7. G is a solid brick, at least 6 vertices. V is any vertex. Then at most two edges incident at V are non-removable in G. Therefore, at least one is removable. That brings us to an interesting question which I haven't thought of earlier. Could it be exactly one removable edge at each vertex? That would mean that the removable edges comprise a perfect matching. Does this actually happen in any solid brick? Let us also take a look at W5. W5, the removable edges are exactly these. And you see that at every vertex at least one. Yeah? And in fact at most two is best possible because you have exactly two everywhere here. Yeah, in the outer vertices, the rim vertices. Let's look at this fellow. The removable edges are basically everybody except the pink edges. All edges except the pink edges are removable. Here the removable edges are the pink edges, so I'm using opposite conventions. Anyways, okay, so that's 10.7, and let me also state 10.8, which I sort of struggled with a bit earlier today. But anyways, it doesn't seem to be too difficult, it's just a matter of spending some time. It seems less motivated unless you see an application, and I think it is actually used in the part 3 of the book, which is on Pfaffian orientations. But anyways, I'll just state it. G is a solid brick. Santosh has probably seen it. Maximum degree 3 or 4. Delta is 3 or 4. Then for every vertex, for each vertex, there exists at most one edge incident with V that does not lie in a removable class. There exists at most one edge in partial of V that does not lie in a removable class. Yeah, that's the result. Anyways, both of these are actually corollaries of what we have proved. I did not write down the whole thing. You have the drawings. This is basically 10.5. It basically tells you that this is the whole drawing and everything, blah 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 blah. When you have two adjacent non-removable edges in a solid brick. Yeah. So anyway, so that's all for today. And everything we did today, we used 10.1, which we never proved. So on Wednesday, we will prove 10.1, which was the first statement we discussed, non-removable edges in a bicritical graph. Right? There's a Delmege-Mendelssohn barrier in G minus E with blah blah properties. So that's what we will do on Wednesday, hopefully. I will finish it, because if I don't finish it, then there will be a very long break. So if required, I may go up to 3 hours, but I'll finish that proof. Okay? And then we have a long break until Amit and Santosh present the paper on 4th of May. Yeah? Okay, that's all for today. Thank you.